Hello and welcome back to Calculus 3, section 13.3 on dot product. Alright, so you already know one-dimensional dot product. 3 times 5 equals 15. That's the one-dimensional, 1D dot product. The goal of this class is to learn two-dimensional dot product and three-dimensional dot product. So the dot product is the way to multiply multi-dimensional quantities. We already said that vector has two qualities to describe it, magnitude and direction. So we are going to take a look at the way to multiply two-dimensional vectors, three-dimensional vectors, and so on. So vector as a mathematical concept is different than, obviously, just a number on the number line. So the product will look a little bit different. But I just want you to know that you already know one-dimensional dot product. So now we're going to talk about two-dimensional dot product. So in 2D, the dot product goes like this. U dot V is vector U, Ux, Uy, dotted with Vx, Vy, to give us a scalar quantity Ux, Vx plus Uy, Vy. You multiply x components together, then you multiply y components together, and you add those together. So that's the dot product for calculation. Now we'll talk about significance and application, but now let's take a look at the basic example. Say you have a vector 3, 4 to multiply with -6 and I ran out of numbers. 1. So you would have 3 times -6 plus 4 times 1, which would be -18 plus 4, for a total of -14. So I'm going to write this in blood over here. Input, vectors, output, scalar, a number. Now, we can use physics to understand and develop the formula for dot product in terms of the magnitudes of the vectors, for vector forces, and the angle between them, because you can push the object on the flat surface forward, and the work done for this motion is work equals force times the distance. Now, force and distance are both vectors. Work is a scalar quantity. Now, what you do here is, if you just go straight, well, in physics, you just learned that work is force times distance, and there are no vectors involved and none of that stuff, right? But the hell breaks loose when you are on the incline, because now you're introducing angle theta. And all of a sudden it's harder to push the object up, right, up the incline. So in this case, we have to take the angle in consideration, which is from where we can figure out what the dot product actually is. So the work is still force times the distance, but now the distance is on the incline, so we can use the cosine of the angle and magnitudes to figure this out. So work is going to be force times the distance, but we can replace these guys with the magnitudes and multiply with the cosine of the angle. So looking at this, we find also a good definition for u dot v as magnitude of u times magnitude of v times the cosine of the angle in between. And I'm going to actually call this formula dot product any dimension. So this formula is good in any dimension because I never specified ux, uy, uz, or u1, u2, 3, 4, whatever. This just has a vector u, vector v as vectors of where the dimension is not specified, and then you have the magnitude. There we go. I have the word asymptote stuck in my head. The magnitude of u, magnitude of v again. So nothing here hints on the dimension we're in, and the reason is this is definition for any dimension. Now, when you look at this here, you can rearrange this equation to get another really cool, really important equation that you can use to calculate the angle between two vectors. And that's important because, right, you have two forces pulling something, or you want to find at which angle they're acting, and so on. So we can rearrange this equation and get cosine theta. Well, let's derive it first. So cosine theta is equal to u dot v divided by magnitude of u times magnitude of v. And finally, the equation that I was after is theta equals inverse cosine of u dot v as vectors divided by u dot v So now we can solve the problem. Find the angle between vector u given as 3, -1 and vector v given as, I don't know, 4, 9, doesn't matter. Go. Make sure that your calculator is in degrees. right, so we have theta equals cosine inverse the dot product of 3, -1, dotted with 4, 9, divided by the square root of 3 squared plus -1 squared, that's the magnitude of u, times the square root of 4 squared plus 9 squared, which is the square root magnitude of the second vector v. This is equal to cosine inverse. Now we have 12 minus 9, and what we have a square root of, this is 10 times 16 and 81, right? That's 97. So 970. So theta is equal to cosine inverse of 3 divided by square root of 970. If I computed that well. So now inverse cosine of 3 divided by 970, 89.82. Is that what you guys have? Anyone? I feel so alone. This is why I'm depressed when I get home. Come on. Someone talk to me.
I got the same math, but on my calculator. So.
You said 85? 3 times 4 is 12. 1 times 9, -9. That's a 3. 3 squared is 9. Plus 1 is 10. 4 squared is 16. Plus 81. 97. So that's 900. Oh, I didn't do the square root of. Oh. Yeah, me neither. Square root of 970. 84.47 degrees. We don't have to go to this precision. We can just 84.5. Well, whatever. So we can find angle. We can find angle between two vectors by simply running this formula and calculating. Now, this has an amazing theorem. If you have two non-zero vectors u and v, two non-zero vectors u and v, can their magnitudes be 0? No, right? So there has to be a value here and it has to be a value there. And if this part here is equal to 0, then the dot product is equal to 0. Now, what angle, for what angle is the cosine theta 0? For what angle is the cosine? Yes, 90 degrees, great. So that gives us this awesome theorem which says that if u dot v equals 0, if the dot product equals 0, then u is perpendicular to v. Theta equals 90 degrees. That's what it means. We're going to use this. So make sure you know that theorem. two vectors are perpendicular if the dot product is 0. Oh, I should say and reverse, right? And should have used if and only if. Okay, I can fix it. I can fix it. Yeah, do this in your notes. There we go. The dot product is 0 if and only if they are perpendicular. If and only if means it works both ways. So sometimes you will have the concept of perpendicular, that means dot product is 0. Sometimes you have the dot product is 0, that means the vectors are perpendicular. Orthogonal, 90 degrees to each other. Orthogonal, 90 degrees. Just in case. Good. Anything else that we should talk about before we hit projections? Okay. So now, for 3D, just add one more component. So the dot product u dot v is now, let's go u1, u2, u3, dotted with vector v, v1, v2, v3. And that's going to be u1, v1 plus u2, v2 plus u3, v3. And that will be the dot product for 3D. So you say you have a three-dimensional vector 3, negative 1, 6 dotted with the vector 0, 9, 4. It's going to be 3 times 0 plus negative 1 times 9 plus 6 times 4 for a total of 0 minus 9 plus 24, which is 15. So 4 three-dimensional vectors. The formula for angle is the same. Now, don't get confused with, let me just get some vectors here, with the direction of a single vector. So we have to address this real quick. When you are in a 2D and you draw a vector, the angle theta here is the direction of that vector. Now in 3D, I told you it's tricky, and you need to know exactly which direction you're looking for, because the vector in 3D has a different angle towards x-axis, different towards y, different towards z. There are things that are called directional cosines and all a bunch of stuff to figure out the direction of the vector in three-dimensional space. So it technically is, you look at the trig, you all have the ability to compute this thing. You just have to see where the vector is in space to draw the triangles and then figure out the angles that you need. So direction of a single three-dimensional vector is not a trivial thing to compute like it is a inverse tangent joke for 2D. Now, in 2D, you also have two vectors like that, vector u and vector v, and then there is angle in between them, theta. So that one you use the dot product to compute. So you have just two vectors in a plane, and the angle between them is this. Now, as I said, for 3D, if you have to draw, if you have to find the angle for a given vector, u, it's technically good luck, right? Because you would have to draw the line and then draw the line, and then there is angle here and angle here, and it's just a whole bunch of angles. You just need to know which one it is, which is why I say good luck, right? There we go. But the 3D angle between two vectors that is the same dot product joke, because the dot product doesn't care about axes or any of that stuff. This classroom is a third-dimensional space. Do we all agree that this is a vector? And here is another vector. So when I join these two vectors, there is angle between them. Now, can I take this and just move it here into a plane? It's still the same angle theta between them. No matter which way I turn these vectors in 3D space, the angle between them is always the same, right? If I don't move the vectors in respect to each other, I can rotate this in space any way I want. So the 3D space doesn't really impact the angle between the two vectors, because I can always put these two vectors on a plane, and even if I rotate the plane, doesn't matter. The angle between the two vectors is the same. So don't confuse the angle between two vectors with the angle of a single vector in a 3D. Because as I said, single angle, right? We use this corner, we said. If I put the vector right here, there is the angle towards this, there is angle towards the other one, there is angle towards z, right? So you need to know which one you want. So that's why one angle, one vector, and the angle, the direction angle, not so much fun, but the angle between two vectors in 3D or 4D or whatever, doesn't matter. You can just calculate the dot product and you're done. All right, we clear that up. Now we have some properties. Property number 1, the dot product is commutative. Shocking, right? It's a product. It's commutative. Number 2, C times U dot V is Cu plus Cv. Oh. No, hold on. I have it wrong. This is the distributive property of multiplication. So Cu dotted with V, which is the same as U dotted with Cv. There we go, much better. So the constant, the scalar, can multiply either U or V first and then the dot product would. So you can do this in any order. And now we get U dotted with V plus W. There we go. Distributive property. That's going to be U dot V plus U dot W. So those are our properties of the dot product. We'll talk about two applications, one of which is projection, the other one is area, and we're done. Take the break after that. All right, so let's talk about projection. Where is the projection? So orthogonal projection. So say you have vector u, and then you have vector v. And what you do is you shine the light perpendicular to vector u, which creates a shadow of vector v, on vector u. You are familiar with the concept of the shadow. If you are not, just raise your hand a little bit above the desk. It will be immediately clear. So what I'm looking for is I'm looking for a vector which is the projection of vector v on a vector u, and u is supposed to give this vector direction and v is supposed to give this vector magnitude. So the red vector that you see over there, what I call the shadow vector, is the vector that has its magnitude given by vector v and its direction given by vector u. So what we are looking for, and this is now the formula, is the projection of vector v onto vector u. So u is the subscript. And that is going to be equal to the dot product of u dot v divided by u dot u, and then everything times u. So let me explain all of the components here. So this part here is a scaling part, and this one over here gives you the direction, because your shadow vector, as you can see on the picture, the red one, is on top of vector u. They have the same direction. You need to scale the vector down. Red vector, so the black v, right, the original vector v, is longer than the red vector, which is the shadow vector, which is a projection vector. It's longer. And you have a scaling factor to bring it down, and the dot product brings in the angle between these two. If you are looking, if you want to see the proof, is in the book, or we can talk after class. So you are able to calculate the projection, and that is used to compute, let's say, work. Remember what I said when I pushed the chair yesterday, that, well, the chair is easy because it's going to roll, but let's say you have a fridge or something, right, that's going to be hard to push. Not for me, but for you. So when I push, if I push at an angle, this vector decomposes into the vector that it's pushing into the ground and the vector that it's pushing forward. So whatever is the vector that it's pushing into the ground, ground pushes up. So that's the wasted energy, right, if I'm pushing this way. If I'm pushing straight, right, then all of my push is going forward and I don't have any wasted energy work, because the force with which I'm attacking when I'm pushing forward is not having any vertical components for the floor to counter that, so I'm not wasting any energy. Now, if I am pushing at the angle, what I'm pushing with is the projection of the vector. So technically that is the force that is acting for the push, and the projection at the 90 degrees of that is the one that is wasted. So we can calculate that by decomposing vectors. We can calculate that also using the projection, which is, depends on, it's like pick your poison, whatever you want. So let's compute one of these. So compute, let's go to homework. I'll just jump into homework. Calculate an orthogonal projection. Vector u is given as 5I plus j minus 5k, and vector v is calculated as negative I plus j minus 2k. Calculate projection of v onto u, and the projection, just to see that it's not the same, of u onto v. This is not commutative. Now, can we just establish this, guys, real quick? Look at the screen. Wouldn't be the common sense if I swap these two, that I swap them all? So every u gets replaced by v, and every v gets replaced by u. So this becomes v, this becomes u, it's the same, but then v, 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 right? So v, 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 or u, 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 depending on which way these guys go. So be careful about that.
great for you.
Sorry?
Remember how you said the bottom 3 lines get cut off from what you can see versus what you can see?
Mm-hmm.
It's because your window, the bar of what windows you have open is at the top and not the bottom. If you moved it to the bottom, it would be.
I can't because I start opening the programs when I touch. It has to be on top.
Maybe on the side.
Then
do
it
that.
takes,
Side of the screen.
then it takes a lot of side real estate.
Now look how much you
Look how much
have.
side real estate you got.
You have a lot.
All right. I win every time. You'll learn that. You'll learn that soon. Everything I do, I thought about it for at least 15 seconds, so it's perfect.
You should just fix it.
That's all perfection takes, 15 seconds.
For
For
me,
everything.
I don't know.
Okay.
For you mortals, hey, at least I said mortals. Usually I say peasants, so it's Calc3. So. Distinguished.
1%.
Yeah, definitely, even less. Okay, so how about this projection of V onto U? So we have vector 5, 1, negative 5, dotted with negative 1, 1, negative 2. And now we need 2 U's on the bottom. That's 5, 1, negative 5, 5, 1, negative 5. And all of this times 5, 1, negative 5 for direction. Great. So the dot product is negative 5 plus 1 plus 10 divided by 25 plus 1 plus 25 dotted with 5, 1, negative 5. So this is going to be 6 over 51 dotted into, well, multiplied by, now this is a scalar multiplication. And we can, I can multiply. So that's 30 over 51, 6 over 51, and negative 30 over 51. So that would be the projection of U onto V. Now projection of vector U onto, no, that was projection of V onto U. Now we have projection U onto V. We still have the same dot product, except now all of these other vectors are V's. And this exercise should show us that it's not commutative. So we have the same dot product of 6 over 51. That, no, lies. We have negative 5 plus 1, so that's a 6 on top. Denominator is different. I can compute it in one shot. So that's 1 plus 1 is 2 plus 4 is 6. So 6 over 6. Negative 1, 1, negative 2. 6 over 6 is 1. So negative 1, 1, negative 2. Great. The second application, calculating work. Problem 44, let's say. The force F, which is given as 432, in newtons moves an object from origin, which is 0, 0, 0, to 860. That's in meters. Find work. So work is what? What's the formula for work? Force times distance. Do you have a distance vector? What's the distance vector? Yes, so distance vector has to be end point minus the initial point. But initial point is 0, 0, so technically the distance vector is just 8, 6, 0 in spiky brackets, because that's a vector, right? Now, this problem would be much more interesting if this first was not 0, 0. They're all 0, 0, so whatever. Work is the force, which is 4, 3, 2, times the dotted with the distance 8, 6, 0, 8 times 4, very good, plus 6 times 3, so total is 50 Newton meters work. That's it. Bye.